Welcome everyone to the 2025 PIBBSS Symposium. Our speaker, Xavier, is here to talk about computational mechanics for Logits. We'll take questions throughout, and you can just raise your hand, and then me or Xavier will call on you. So.
All right, yeah, thanks for the intro, Carlo. Today, I'm going to be talking a little bit about my PIBBSS project that I completed this summer under the supervision of Adam Shai and Paul Rikers. And the aim of the project was to try and understand modular addition from the perspective of computational mechanics. And what that sort of led to was the development of new generative processes and new computational mechanics tools that allowed us to attack problems at the level of the logits as opposed to the probabilities. And so the talk today will try and be essentially trying to make sense of these objects. So to give you a brief outline, I will give you just enough computational mechanics. I'll introduce the generative processes that we'll be considering today. We'll introduce a hidden Markov model and sort of a new version of a generative process that's sort of inspired by the hidden Markov model. But instead of producing probabilities via a linear dynamic, it will produce instead logits by a same analogous linear dynamic. And then we'll derive computational mechanics properties from this, like predictive vectors. And then we'll sort of apply this general framework to the problem of modular addition. And then we'll present some results to give some suggestion that actually there's something interesting along these lines going on inside of transformers trained to do modular addition. And then if we have time, I'll give some outlook and yeah, some future work that would be interesting to continue. So now I'm sure many of you in the audience are familiar with these objects, but we'll define them here as a sort of a context setting exercise. So we can think of a hidden Markov model as consisting of a set xi here, or calligraphic x, which we think of as sort of the vocabulary of emissions of our generative process. So these will form sequences through different steps of the hidden Markov model, and a collection of transition matrices that are indexed by the token emission, and where the matrix elements of these transition matrices correspond to the probabilities of if you're in a state Si, transitioning to another hidden state Sj, and emitting the token X in the process. So we think of the transition matrices as sort of defining the dynamic of state transitions and corresponding emissions of the process. So if we fix some initial distribution over hidden states of the process, then we can associate a probability to observing the following token sequence W1 through Wn, and it's given in this rather nice factorized form. And one of the aspects that's nice about this factorized form is that we can sort of generate this process just via simple linear algebra. So we define this state, which corresponds to the initial distribution over hidden states, and then each of these probabilities is then associated with just multiplying by the transition matrix and taking this very particular matrix element. And so this sort of motif will occur again throughout the talk. And we think of the hidden Markov model assigning probabilities via this linear dynamic. And so the nice thing about hidden Markov models is that they like facilitate this very graphical notation. So here, for this example, we have three hidden states, S0, S1, and SR. And as we transition from state S0 to S1, we emit the token 0 with probability 1. As we transition from S1 to SR, we emit the token 1 with probability 1. And as we transition from SR back to S0, there's some 50-50 probability of emitting the token 0 or emitting the token 1. So in this case, our vocabulary is 0 and 1, and our transition matrices are spelled out on the right-hand side there. So now we've sort of like defined these objects of study, these simple generative processes. We can then ask like a very computational mechanics-y question. So what information about the past in this process is relevant to predict the future? And so a natural setting to consider this question is by looking at conditional probabilities, where we condition on observing this past token sequence, W superscript P, and then we see what's the probability of observing this a future token sequence. And so we can do sort of a Bayes rule type thing in the central equality here. And by expressing this expression in terms of our underlying EHMM linear dynamics, we have this expression on the right-hand side. And here we see a natural partition between the past, or objects from the past, and objects from the future. And that sort of motivates our definition of the predictive vector as this sort of vector that's normalized by these past observations. And by plugging this vector back into the probability, then we see that it's this vector that plays a role in all future predictions. Another way to view this vector that's not completely obvious from the math I've laid out here is that this vector corresponds to doing Bayesian updating over the hidden states of your process, given the observation WP. So now I'll make two observations. So the first is an empirical observation. So that is from this Shai et al. Paper, where the predictive vector of the EHMM is often linearly decodable from the activations of the neural network trained on data from the EHMM. So this is like somewhat surprising and gives you sort of a sense that this computational mechanics framework is relevant to, for example, neural networks that are performing next token prediction. And the thing that's like particularly interesting is that the predictive vector is linearly decodable. So it's as simple as it could possibly be. The second observation is that transformers and other neural networks often produce probabilities by passing the output of the final hidden layer, which are like essentially a vector of real numbers, through a pretty intense nonlinearity. And this intense nonlinearity is the softmax function. So we call these ZWs here the Logits, and those are from them we create a probability distribution via the softmax function. And so the physics literature is very familiar with this object, and in that context, it's called the Boltzmann distribution, where the Logits correspond to negative energies. So a natural question arises, is that, like, can we develop a notion of an HMM, a generative process, that produces Logits via a similar linear dynamic, and that also admits analogs of the predictive vectors, so these nice computational mechanics objects? And the answer is yes. And the particular structure that admits these nice properties is what I call here an energy-based hidden Markov model. So an EHMM consists again of a set together with a collection of transition matrices H superscript X, and an initial vector eta and a final vector phi here. And the condition on these objects is that this particular matrix element, where here again this HW is a product of HW superscript W1, W2 through Wn. So this is our like token sequence, such that this particular matrix element is real for all n length words, and where n can run over the integers, or over all the natural numbers rather. And so these conditions allow us then to consider this particular matrix element, this ZW here, as a logit, which can then be turned into a probability via the softmax function. So again, we can ask the similar Comp-mech question: what in this process information about the past is relevant to predict the future? And again, the natural setting is to consider conditional probabilities and the corresponding conditional logit, this Z object here. And what I mean by a conditional logit is the logit that when passed through the probability, when passed through the softmax, gives you the probability distribution, the conditional probability distribution. And so I claim, famous last words, that the proof of the following statement is easy. So the conditional logit can just be stated as the joint logit. Okay, so now the stage is set for us to run the same process again. So we consider the conditional logit. We express the conditional logit in terms of our our generative process basic elements, the initial vector, the final vector, the transition matrices. And we see, again, a natural partition between the past and the future. And then we group this crucial information about the past into the predictive vector. And we see that just in like direct analogy with the HMM case, the predictive vector is can be expressed in the conditional logit in exactly this way. So here is like a checkpoint in the talk where up to this point, I'm going to summarize the key bits of data. And if this isn't clear, now is like a very nice time to address it. So far, we've introduced two processes, a hidden Markov model and an energy-based hidden Markov model. For the HMM, the output is probabilities, and these probabilities are produced via this linear dynamic. And the corresponding predictive vector, this computational mechanics object, is given by this functional form on the right here. On the other hand, the EHMM, it produces, instead of probabilities, it produces logits by the exact same linear dynamic. And its predictive vector is again given here on the right-hand side, and its functional form is slightly simpler than in the HMM case. So let me just pause here, take a drink, and if we have any questions, we can address them. Otherwise, I have some questions of my own. Yes, Yasmina.
Hi, Xavier. I'm wondering, I mean, maybe you explained this already or it's clear, but why does the EHMM not have a normalization like the HMM?
Yeah, that's a really good question. So I think the answer of this question stems from the fact that let's go back. The Boltzmann distribution is invariant under constant shifts of the logits. So naturally, you would expect that the logit is like kind of like, you can think of it a little bit like a log probability. So this normalization, you may expect it to show up as like you add an additional constant. But it turns out that the softmax is invariant under this constant, and you can just ignore the constant. And so it has this slightly simpler form without that normalization. But yeah, that's a really nice question.
Thanks.
Okay, so I've introduced all this machinery. It's a little bit heavy. We have natural questions. So is this formalism at all useful? Do neural networks represent the predictive vector of the EHMM? And another follow-up question, if the answer is yes, if the neural network is given a choice, if there's two processes that are like close by in process space, does it have a preference over one or the other? Will it choose to represent the predictive vectors of the EHMM over the HMM or vice versa? And we'll try and gesture at answers to this question in our application of this formalism to the problem of modular addition. So the classic problem of modular addition, we look at two numbers, a plus b, and what is the modular sum, c, if we fix our modulus p. And so I claim that the natural algebraic structure underlying modular addition is given by the cyclic group. And we can consider the cyclic group CP as being generated by a single element R subject to the one condition that R to the power P is given by the identity. Where on the right-hand side, if we like, we can think of the identity as just R to the power 0. And so this statement here is what I mean by it algebraically encoding modular addition. We have this equality inside of our group if and only if C is equal to A plus B mod P. So now another like slightly technical thing that we'll define, which will allow us to define the transition matrices for our processes is this notion of a CP action. So a CP action is essentially an action of our group on a set, and it's an action that it's an action of our group on a set that essentially respects the group structure. So if we act by this group element RA plus B on an element of our set V, then that is the same as first acting by A and then acting by B. And we look at two particular group actions. And this looking in this direction is heavily inspired by this Changtai et al. Paper, Toy Models of Universality. So the first action we consider is the action of our cyclic group on elements of the set CP, where these E vectors here are row vectors that they're essentially one hot row vectors that are p-dimensional and have a 0 in all other elements except the ith element. And so geometrically, we can think of elements of this set CP as parameterizing vertices of a p-1 simplex. So a very high dimensional simplex, these are like the extremal points. So this CP action here induces the following matrix representation, where essentially we encode the structure of the group in terms of linear algebra, in terms of matrices. And for this case, the group element is this these like cyclic circular matrices, I believe, is the terminology. Now we consider another action. So the first action we'll use to define our HMM, and the second action we'll use to define our EHMM. So here we consider the action on this elements of the following set here to the right, where the vectors from this set correspond to two-dimensional vectors with these trig functions in them. And so geometrically, we can think of this set as parameterizing vertices of elements of a p-gon in the plane. So a polygon with p vertices. Each vector corresponds to one of these vertices in the plane. And so just like above, this action induces a matrix representation. And in this case, it takes this form on the right-hand side here. Okay, so now so again, that was like rather heavy machinery. Now we'll give some intuition for the HMM that corresponds to modular addition. So in this case, the vocabulary consists of values from 0 through to p-1, where we fix p, and the following hidden states. So there's three natural classes of hidden states. So the initialization state here, the yellow, the states after the process emits the first token, the states after the process emits the second token, and then finally, we rotate back to the initial state. But intuitively, we can think of this random mod p process as first, we initialize in the state s superscript 0. Then we sample a random value uniformly from our calligraphic X set and transition from the state S0 to SA, indexed by the token that we emit in this transition. Then we again sample another element from our set calligraphic X. And in doing so, we transition from our state A to the state SA plus B mod P. And in doing so, we emit the token B. And finally, we transition from this blue state to the again the initial state and emit the token C, where C is exactly the this sum A plus B mod P. So to reiterate, the process goes as follows. We initialize, we sample an A, transition to a state, emit an A. We sample a B, transition to a state, emit a B, and then uniquely transition back to the initialization and emit the modular sum, the C. So we have two examples for the case where P is equal to 4. So let's start on the left-hand side. We transition from the initial state to the hidden state indexed by 2, emitting a 2. We emit a 3 and then transition to the modular sum 2 plus 3 mod 4, which is 1. And then we transition back to the initial state and emit a 1. And we have another process down below. So that's some intuition for the process. Formally, the random mod P HMM is defined. The transition matrices are defined in the following block, the block form here, where we collect all of the states corresponding to initialization, first random, second random, and these blocks here correspond to the representation induced by the action of the cyclic group on the the P-1 simplex. So all that to say is that these blocks have been carefully chosen in such a way that the following matrix elements are equal to the right-hand side, which I'll go through. So the probability of emitting a token A here, calculated through this linear dynamic, is 1 on P. So this is a uniform distribution sampling tokens from our vocabulary. The probability of emitting AB is again going to be uniform over AB, giving P 1 on P squared. And finally, the probability of producing ABC is going to be uniform for A and B, but then unique for the correct answer C. So all of the probability is going to be concentrated on this C, for which A plus B is equal to A plus B mod P is equal to C. So now, again, we can reuse parts of the previous calculation to identify the predictive vectors of this random mod P process. And in doing so, we see that after observing token A, it's this elementary vector sitting in this central position. After AB, it's this elementary vector corresponding to A plus B mod P sitting in this right position. And after ABC, we go back to the initial vector, which is essentially a point in a 1D subspace that we don't care about. So by projecting out the 0 entries, the set of predictive vectors just corresponds to the points on the P-1 simplex. These elementary vectors here in this set. So that was the random mod P process, the process that exactly corresponds to modular addition. Now we're going to define an EHMM process that approximates this HMM process. And so accordingly, we call this process the soft random mod P process. And again, it consists of the same vocabulary, but instead of containing hidden states, we think of the role of the hidden states being now taken up by these vectors, which are parameterizing the points of a p-gon in the plane. So intuitively, the soft random mod P EHMM is given by the following. We initialize in the vector eta here. We sample uniformly from our vocabulary and transition from this initial vector to the vector indexed by A. We then sample again uniformly B from our vocabulary and transition from the vector indexed by A to the vector indexed by A plus B. So this is our modular sum. And in doing so, we emit the token B. And then finally, we transition from this A plus B vector back to our initial state, but we and emit the token C. But in this case, all of our probability isn't concentrated on the correct answer. There's some probability distributed over the entire set of answers, our entire vocabulary. But the only condition that we have is that the probability assigned to the correct answer is the largest probability. So it absorbs most of the probability mass. And so the idea is that we could parameterize our soft random mod P process such that we get an arbitrarily good approximation of modular addition. So we parameterize our random mod P process by a tuple of frequencies, where the frequencies take values in the following set. And now we can define formally the EHMM. And we do so in a very analogous way to the HMM, where our transition matrices are have a block structure, again, where the blocks correspond to the particular order of emissions, and where the vectors and matrices correspond to those induced by the group action of the cyclic group on the vertices of the p-gon in this particular case. So now, as in the random mod P process, we now are using our linear algebraic objects to verify that they produce the logits that we would like. So the logit corresponding to the emission A is assigned the value 0, which essentially corresponds to a uniform distribution over token emissions. Again, the logit corresponding to AB is 0, while now the logit corresponding to the emission A, B, and C is this sum of cosine functions, where we note that when C is equal to A plus B mod P, check the argument of the cosine here, the logit is the largest, and it's smaller for the other values. So we'll point out here that these are the empirically these logits have been empirically identified to correspond to the logits of transformers trained to do modular addition. And this is this classic Neonander paper, Progress Measures for Grokking via Mechanistic Interpretability. And so just to give a little bit more intuition here, for the correct answer, these sums of cosines will constructively interfere, boosting the value for the correct answer, and will destructively interfere for the incorrect answer. Okay, so now we can pass these logits through the softmax function to produce probabilities. And so for the emissions A and AB, these correspond to the uniform distribution over our vocabulary, which produce 1 on P and 1 on P squared. And finally, the probability associated with the logit corresponding to ABC is this big complicated mess. But intuitively, we can just think of it as the largest logit value corresponds to the correct answer. And so that will concentrate the probability on the correct answer. And so to give some sort of intuition for this fact, on the left-hand side here, I've plotted the value for the logits if we assign them the values of this expression I've derived, I've got here on the left-hand side, and on the right-hand side is the corresponding probability associated with those logits, where the correct answer corresponds at this x equals 0 value, and here we can see it's much larger than the other x values. I'll also mention that we can then boost the coefficients associated with the cosine function, essentially bloating the logits, and that will act to increase the probability associated with the correct answer on this right-hand side here. So if we recall the EHMM predictive vector equation, we can reuse parts of the previous calculation to essentially characterize the predictive vectors for this process. And a little bit of annoying calculations will let us arrive at the following forms of predictive vectors. So here we have in the center these direct sum, so a concatenation of the p-gon points, the points on a p-gon after observing A, the same thing after observing AB, and then finally after observing ABC, we have this trivial one-dimensional vector. So if we project out the 0 entries, then the interesting set of predictive vectors will occur after observing A and observing AB, and will be elements of this set. So will correspond to essentially subspaces that contain essentially p-gons in the plane. So many copies of p-gons, each parameterized by different frequencies. So again, here's another checkpoint of the talk. And if there are any questions, now would be like a decent time to resolve them. Let me summarize. So we've defined two processes, the random mod P process, that's an HMM, and the soft random mod P process, that's an EHMM. So for the random mod P process, this corresponded exactly to modular addition, and the corresponding predictive vectors sat or sit on the vertices of a p-1 simplex. On the other hand, we have the soft random mod P process, which approximates modular addition. And in this case, the predictive vectors of the process corresponded to many copies of a p-gon that sits in 2 dimensions. And so if there are not any questions, again, I have some of my own. The question is, if you train transformers on the problem of modular addition, what are their internal representation? What do their internal representations look like? So we have a little bit of a tension here. So on the one hand, the computational mechanics story tells us that models trained on a particular HMM, trained on a particular generative process, will represent internally the predictive vectors of that process. On the other hand, we have this Nander et al. Result, which states that the logits of the transformer take the form that are suggested by this soft random mod P process. And so we're going to essentially examine the question, what do the models, we're going to resolve the tension by investigating what the models represent in their activations. So we have the following recipe. We first train a very simple, the simplest possible transformer, 1 layer, 1 attention head, to grok the problem of modular addition, which essentially involves training the transformer on the random mod P process. Then we're going to fit the logits of the transformer to determine the free parameters of the soft random mod P process. And then we're going to study what objects are linearly represented in the model activations by both linear regression and PCA, principal component analysis. So first we find the frequencies by doing Fourier analysis on the unembedding matrices of our transformer, and we identify this sort of sparse representation in the Fourier domain of the weights of the transformer, and then we use these to fix the frequencies of our process. So in this case, we have 5 frequencies corresponding to 30, 18, 36, 38, and 41. And then first, on the left-hand side, we take the activations of our trained transformer post MLP, pre-embedding, and then we perform linear regression to, on the top, the predictive vectors of the HMM process, random mod P, and then on the bottom, the soft random mod P process. And so by looking at this plot, we see that throughout the process of training, we always get a far better fit of our activations to the EHMM predictive vectors, the predictive vectors of this new generative process that we've defined here. This is the supervised analysis, and we supplement it with some semi-supervised analysis. So with the knowledge that there are 5 relevant frequencies, we perform a PCA on the same activations, post-MLP, pre-unembedding, and we look at the top 10 principal components, which achieve an explained variance of 0.89. And then we perform linear regression to the theoretical predictive vectors, and we achieve this plot on the right-hand side. So on the right-hand column, we have the post-processed activations, and on the left-hand side, we have the corresponding theoretical predictive vectors that are suggested by our process. So an interesting observation here is that the activations on the right-hand side, the p-gon, the copies of the p-gon, all have some non-trivial width. And there is some results in the literature that suggest that this is due to some peculiarities of the MLP. Of course, these results apply to a toy transformer, namely a one-layer, one-headed transformer, and these results seem to rhyme a lot with these recent results by Cantaniemi et al. This is Max Tegmark's group that study models, the activations of production level models that are doing addition. And so they find that there are representations of p-gons in the activations of these production level models. So these are the representations on the top row here, in addition to some linear term. So this is this bottom thing here. So they describe this as a generalized helix, where the relevant frequencies are 2, 5, 10, and 100. And so my claim is that if we instead looked at, this was looking at just straight out addition. If we look at modular addition, I claim that the activations of the transformer will just correspond to these p-gons on the top here and not have this linear component to it. So here's a bonus slide. If we perform the analogous semi-supervised, the semi-supervised analysis we performed post-MLP pre-unembed to the activations post-embedding. So this is we one-hot encode our vocab, then we embed, and we look at the activations there. We see that even there, the model chooses to represent the activations, or that rather that the predictive vector of the soft random mod P process is represented even that early in the model. And this is true after observing the token sequence A, and also, so this would be the predictive vector corresponding to eta A, and the same is true after observing token sequence A and B for eta B. We can now draw this. We now draw this picture of the various interesting positions of our transformer and the activations at these positions. What do they linearly decode to? So, as I mentioned, after the embedding of the tokens, immediately the transformers represent the predictive vector corresponding to A and the predictive vector corresponding to B. The simple attention mechanism just adds these two predictive vectors. So we get VA plus VB, And then the MLP turns this vector, in addition to the skip connection, into V A plus B mod P. So this is a rather strong suggestion that it's the predictive vectors of the EHMM that are represented inside the transformer doing performing modular addition. So now let me briefly provide some outlook and some directions for future work. So we currently have the situation where we have our model that is trying to predict the token distribution that is determined by some generative process. It turns out that if we pick the generative process very specifically, there is a nearby generative process that is constrained by the original that determines some approximate predictive vector. And it is this predictive vector that the model chooses to noisily represent and uses this predictive vector to decode the corresponding token distribution. And so some natural questions arise from this work. So we can think of the random mod P process as sort of a generalization of a well-known process in computational mechanics. This is this random XOR process, if anyone's familiar with it. For P equal to 2, the processes are equivalent because addition mod 2 on bits corresponds to the XOR operation. And there are interesting dynamics when you consider the random XOR process initialized in the stationary distribution. We've picked a very synchronized distribution to study modular addition in, the random mod P process. It would be interesting to study the types of predictive vectors that arise when you initialize instead in this stationary distribution and not in this synchronized state. So in that case, the class of predictive vectors is much larger, and the problem becomes much more difficult for the transformer to model. And then the natural question would be whether the model still decides to represent the predictive vectors of the soft random mod P process, as opposed to the actual process the model is trained on. So I also claim that EHMMs are sort of independent interest, and it would be nice to push more in this direction by directly training models to predict data from EHMMs. And a natural question would be to look at the activations of such transformers and see whether the predictive vectors are linearly decodable from activations in this setting. And so finally, another thing that would be interesting to consider would be to look for other HMM processes that have a corresponding or underlying EHMM process. And a natural candidate would be the MES tree. We know the MES tree encodes representations of the HMM that look a lot like the predictive vectors. So in this case, we would imagine that the EHMM predictive vectors would have to look a lot like the HMM predictive vectors. But with all that said, thank you very much for listening, and I'm happy to take any questions you have.